Assalamu alaikum. I welcome you all to another lecture on electrical machines. We were discussing the torque speed characteristics of an induction motor, and in that aspect we derived the expression for the torque speed characteristics of an induction machine. In that characteristic we studied that the initial torque, which is the starting torque of a machine, is slightly higher than the rated torque of an induction motor, and therefore a motor is capable of taking any load which is equal to the rated load on a given machine. Because at the start the motor is at standstill, and at the standstill the mechanical power is equal to 0, and therefore the starting torque is very important for the induction motor torque speed characteristics. So in this aspect we studied that we have here we have this torque. This is the torque speed characteristics. It was something like that. We have the torque speed characteristics of an induction motor. Now, if for some reason, if the rotor speed exceeds the synchronous speed of a motor, then the direction of the torque reverses and the motor starts to act like a generator. And consequently, the motor behaves like a generator, and it moves into this particular region, which is known as the generator or generating region, where this is the and synchronous, and this is the torque induced. So you see that if for some reason the rotor is accelerated or rotor moves at a speed which is more than the synchronous speed, then the direction of the torque reverses and the induction motor becomes a generator. Now there is another case. What happens if for any reason the three phases which are supplied to the stator of an induction motor are reversed such that phase B and C, or any two phases, are interchanged with each other? Now if we have a sequence, let us say that the supply has an ABC sequence, and you switch the two, or to swap one of the two phases of this ABC sequence such that we converted it to ACB, then instantly the electrical field which is created inside the stator, it will turn its direction, or it will reverse its direction instantaneously, because the electrical system has much faster dynamics compared to a mechanical system. Now because the direction of the synchronous speed or the field has reversed, the rotor requires a finite time to reverse its direction, and therefore what happens is that it decelerates very fast. This is an important factor that is used to brake the motor and is called the braking of the motor. So this is the braking region here. Here we have the braking region. This braking region, phases are swapped. Two phases are swapped to reverse the direction of the electric field. The phase reversal or phase sequence reversal is called plugging. So this part, which is the motoring part, we have already discussed this in pretty much detail. Now in this particular lecture we will try to go further to see what is the maximum torque that a motor can achieve at any given value of the slip, and thereafter we will discuss the methods through which the equivalent circuit or the parameters values of the equivalent circuit of an induction motor can be established. So these are the two tasks that we shall undergo in this particular lecture. Now before we move further, the first task is to see what is the output power characteristics with respect to the speed of the motor. So if we have, for example, let us say that here we have this is the P converted. Now the converted power, which is converted into a mechanical domain, is equal to torque induced into this omega m. So what we shall do here is that we will plot this power converted power on the same graph to see how much it differs from the torque speed characteristics of an induction motor. So at the start, this omega m is 0, and therefore it will start from this particular point, and then as we move along this speed axis, as we move along the x-axis and the y-axis simultaneously, we get this type of a characteristic curve here. Notice here there are two important points to notice. The first thing is that the maximum power that a motor can supply is not corresponding to the point of the maximum torque that a motor can supply. So you see that here we have this is the breakdown torque or the pull out torque, whereas this point is the maximum power that a motor can convert into mechanical domain, and it is not corresponding to the maximum value, rather it is corresponding to a value which is somewhere here. So this is the speed corresponding to the maximum power, Np max, and this is the torque which correspond to the maximum power, and both of them are different than the values of the speed and the torque that we obtain during the torque speed characteristic curve. And of course, with this particular curve, we come to know that no power is converted into mechanical form when the speed of a motor is equal to 0. Now, in the last class, we discussed that this torque induced is equal to the PAG divided by the omega synchronous, which means that the torque induced, which is equal to the air gap power divided by omega synchronous, it occurs when we have the maximum air gap power available. So the maximum air gap power, PAG, it will be consumed when the resistance which is present in the rotor circuit, when it consumes the maximum power. So this means that what I am trying to say here is that in this particular circuit, we have this JXR or X2. Here we have this R2 over S, and this one we are feeding the air gap power to this rotor circuit here. To have the maximum value of the induced torque, we have to maximize this air gap power, and that can only be ensured once this R2 over S gets the maximum power consumed in it. For that, we will revert back to the Thevenin equivalent circuit that we have studied, and thereafter we will apply the maximum power transfer theorem, which says that the maximum power in any given circuit or any given load occurs when the load resistance becomes equal to the Thevenin resistance of the circuit. So let us draw the Thevenin equivalent circuit again. Here we have this V Thevenin, this is the R Thevenin, and here we have the JX Thevenin. Here we have this one is the JX2, and this is R2 over S. Now, if this R Thevenin becomes equal to this R2 over S, then according to the maximum power transfer theorem, the maximum power is delivered from this V Thevenin to this load, which is this R2 over S. So what is the total source impedance? That source here is equal to R Thevenin plus GX Thevenin plus JX2, and we are treating this part as the load part, and the rest of the part is this all correspond to the source part. So this Z Thevenin, the source, which is this one, that is equal to R Thevenin square plus X Thevenin plus X2 whole square. To ensure that the maximum power is consumed in this R2 over S, this Z source is equalized with the value which is equal to R2 over S. This is the same condition which is outlined in the maximum power transfer theorem. Now solving this equation for the value of slip, then S is equal to R2 divided by R Thevenin whole square plus X Thevenin plus X2 whole square. This expression gives us the value of slip. Corresponding to this value of slip, the maximum power is transferred to this R2 over S, and that corresponds to the maximized value of the air gap power available inside a motor. And with that value of the PAG, the maximum torque which is induced in a motor can be established. Now, one thing we have seen here from this particular expression, that the slip S is directly proportional to the value of the resistance R2. And this is something which provides an edge to the wound rotor induction motor compared to a squirrel cage induction motor. Because in a squirrel cage induction motor, the rotor is formed such that we do not have any external connection with the rotor circuit. Whereas in a wound rotor induction machine, we have arrangements such that the value of the rotor resistance R2 can be altered and can be varied through external connections. And therefore, by using the external connections, we have a provision that the slip can be varied for that particular machine. And this is a clear advantage of the wound rotor induction motor over the squirrel cage induction motors. So the maximum torque, tau max, can be written as by using this expression, and substituting it back in here, we get the tau maximum, which is equal to 3 times V Thevenin square divided by 2 omega synchronous R Thevenin plus R Thevenin square plus X Thevenin plus X Thevenin X2 whole square. So this is the value of the maximum torque that a motor can actually provide. Now these two expressions, this one and this one, they are very interesting and provides very good amount of knowledge about an induction motor. The first thing is that the maximum torque which occurs on a machine is independent of the rotor resistance. The second point is that the maximum torque corresponding to a value of this slip can be varied with this resistance R2. What does this mean? This means that we can have the maximum, without altering the maximum value of the torque, we can add external resistances to an induction motor to shift the maximum torque or the pull-out torque to lower RPM values as well. For example, let us say that we have this is the torque speed characteristics of a given machine, and we have the rotor resistance equal to this R1. Now if we increase this R1, then what happens? That by increasing this R1, the slip also increases. If the slip increases, then the torque which is available somewhere here, this is the maximum torque line, it will shift onto this side, and corresponding to the same value of the maximum torque, the starting torque has actually increased. This is the torque 2, this is torque 1, this is the tau maximum, which is same for both the cases. However, for this R2, the starting torque is actually increased. So what we are inferring here is that if a motor is provided a load that requires a higher amount of torque, then the same motor can be utilized by actually inserting the external resistances into the rotor circuit. And this is only possible for the wound rotor induction motor, where we have arrangements for the external connections with the rotor circuit. It is not possible with the squirrel cage induction motor. Similarly, if we further increase this R2, then this becomes like this one. This is this R3. Here we have this one is this R4, and for all the resistances here, this R1 is less than this R2, is less than this R3, and this is less than this R4. Now, without altering this maximum value, this is the maximum torque. The maximum torque is the same, torque maximum is the same, but we have certainly achieved larger starting torques for these increased value of the resistances. Now, once the motor starts with these increasing torque, the heavy loads can be adjusted, and thereafter these resistances can be plugged out of the system so that the motor operates under the normal operating conditions. Now, the variations in these torque speed characteristics of an induction motor give us an insight about the efficiency of a given machine. Now, you should notice here that the starting torque increases with increase in the rotor resistance R2. Higher the rotor resistance R2, more is the starting torque. However, this increases the slip as well. So this R2 is, when it increases, then the slip also increases. Now, what is the impact of having these arrangements on the efficiency of an induction motor? Now, notice that the converted power, which is converted into a mechanical form, is equal to 1 minus S into this air gap power that we have derived in an earlier lecture. Now, this shows that more the value of the S, less is the power which is converted into a mechanical form. Lower is the efficiency of a motor. After all, the efficiency of an induction motor is the measurement of how much of the electrical power is converted into a mechanical power. Now, with the increase in the slip value, we are compromising on the overall efficiency of the converted power, P converted, and therefore we should always see the impact of the slip and the adding resistances in a given machine to accomplish a given task, because there is a compromise between the two is required. We require to have a higher starting torque. Okay, we can increase this resistance R2, but that increase in R2 also results in the increase in the slip value, and the increase in the slip value decreases the converted power on the mechanical domain side, and therefore the efficiency of the motor decreases with the increase in the rotor resistance R2. Vice versa, a motor with a lower value of the rotor resistance has a higher efficiency, but it will have an impact on the starting torque values. So a compromise is required between the two, and one solution is that we have already discussed, is that we use a wound rotor induction motor and we connect the resistances only during the startup value and we take them out of the circuit. The resistance can be removed so that the motor operates at a lower slip value, so that we can maximize the converted power in an electrical induction motor. So we have the more the value of the slip, less is the P converted. So as the value of slip increases, the P converted decreases, and hence the efficiency of the machine still decreases, right? So vice versa, if this R2 is low, then we have a lower slip value, and therefore this P converted will increase, and this is an indication of the increase in the motor efficiency. So between this point number 1 and this point number 2, we have a compromise is required. A compromise is required between 1 and 2, and mostly this is done by automatic circuits that control the starting torque of an induction of a wound gauge induction motor. They insert the resistance in the circuit, and after some time, when the starting phase is gone, they remove the resistance so that the motor operates at a lower slip value, and hence the efficiency of a motor is achieved. So far we have thoroughly discussed these torque speed characteristics. Let us move on to the induction motor tests, which are performed to identify the parameters of an equivalent circuit. So we have for finding the for determining the circuit parameters, for determining these equivalent circuit parameters, we want to have certain tests which are used to perform the resistances of the stator winding, the R1, the the resistance of the rotor circuit, this is R2, as well as the admittance of the equivalent circuit, which corresponds to this X1, X2, and the magnetizing branch XM. These values are calculated through various tests which can be performed on an induction motor following the international protocols such as this IEEE standard number 112, which deals with the procedures for undergoing the test of an induction machine. So the first test in this regard is this no load test. In a no load test, we have no load on the motor. We measure the current for all the three phases while having a variable three-phase variable frequency. We have a variable frequency and voltage three-phase supply. Before we connect it to this ammeter, we have an arrangement that measures the power P1 and this power P2, so that we can measure the three-phase power here. So 2 wattmeters are enough to measure the power in a three-phase circuit. Also, we measure the voltage between the two phases. So with this arrangement, we intend to find out the rotational losses of an induction motor. Rotational losses are those losses which occur because of the friction, the windage, and the stray losses. So not only we get two types of information from this no load test. The first one is the rotational losses, and the second is the magnetization current. Now, because this motor, it is at no load, with this no load means that the motor operates nearly at the synchronous speed with no mechanical load. Only P, F and W, which are the friction and windage losses, they are present. So this I2 is approximately equal to 0. I2 is very low because the motor operates at nearly synchronous speed, so the slip is very low. Now, because the slip is very low, the R2 over S is very high, and therefore this I2 is negligible. That we have discussed very thoroughly in the previous lecture. Now, if I draw the equivalent circuit of an induction motor, here we have the R1, this is JX1, here we have the resistance RC, this is JXM, here we have the JX2, this is R2, and this is R2 1 minus S over S. This R2 represents the rotor copper losses, while as this R2 1 minus S over S represents the power which is converted into the mechanical domain. Here we have this V5, this is the current I1, and this is the current I2. Now, under these no load conditions, we said that the value of slip is very low, and therefore this I2 is approximately equal to 0. So, this R2 into 1 minus S over S is very large compared to the value of this R2 and this GX2. So we can modify this circuit. So because the slip is very low, right? It is very low. it is nearly equal to 0.001 because we are operating at the no load condition. For this given circuit, this R2 into 1 minus S over S is very large compared to this JX2 and this R2. Both of the rotor equivalent parameters, they are very negligible compared to this R2 into 1 minus S over S. And therefore, we can modify this circuit by having only this RC. This is JXM. So this is the modified circuit. This is the V5. This is I1, R1, JX1, and this resistance is only left, which is equal to R2 into 1 minus S over S. So this is the modified equivalent circuit under the low load testing conditions. Now we are also measuring the power here for this no load test. We are measuring the amount of current which is flowing into each of the stator phase. So based on these two informations, input power measured by the meter in this no load test must be equal to the losses which are occurring in the motor. By this I mean that under these tests, the stator copper losses PSCL, which are equal to 3I1 square into R1 can be calculated. Now once we get the power from these power meters that we have installed in this particular test, then the input power P in is equal to P stator copper losses plus P core losses plus P F and W plus P miscellaneous or the stray losses. Now this PSCL, this can be attributed as the 3I1 square into R1 plus the P rotational losses, that can be written as P ROT. Now in here, with this value of the input power, the current which is needed to establish a magnetic field inside this machine is large because of the reluctance which is available in the air gap. Remember that the reluctance is the resistance in the magnetic path. Reluctance is the resistance in magnetic path. So what happens with this high value of reluctance? That this XM is much smaller compared to the resistance which comes in parallel in this particular branch, and therefore the input power factor is very low. So with large lagging current, the voltage drop will be across the inductive component such that the Z equivalent is equal to V5 divided by I1 at this no load, and that is approximately equal to the value of this X1 and this Xm. Remember that this current I2 is approximately equal to 0. So we are not bothered about the current which is flowing through this branch, which is the P, F and W. So this Z equivalent is this phase voltage divided by the impedance, and because these values are dominant here, so the Z equivalent can be equated as equal to this sum of the X1 plus Xm. Now if X1 is calculated, then the Xm can be known, right? It can be known. The second test in this regard is the locked rotor test. In the locked rotor test, we again have the similar type of arrangement. for example, we have the current here. This is P. Here we have another ammeter for this phase and another ammeter for this particular phase. This is P. Here we have the voltage V, and we have again the same sort of the supply, which is a variable frequency, variable voltage, three phase supply. And here we have this IA, this is IB, and this is IC. In a locked rotor test, the rotor is locked so that it cannot move, and therefore the slip is equal to 1. With the slip equal to 1, we have the rotor frequency equals to the electrical frequency which is supplied here, and that is equal to test frequency here. This test is similar to that of the short circuit test of a transformer. We apply the voltage through this variable frequency, variable voltage three-phase supply, and we measure the power, voltage, and the current for this three-phase motor. So we slowly vary the applied voltage. We slowly vary the applied voltage such that the current reaches the rated value, rated full load value. Thereafter, we measure the voltage, the current, and the power. They are measured. So the equivalent circuit for this machine test is, we have this one R1, this is JX2, this is JX1, sorry. Here we have this one equal to JX2, and this is R2 over S, which is equal to R2 because the slip is equal to 1. And in here we have the JXM as well as this RC, this is V5, and here we have the current I1 here. This is the current I2. Now, if you notice onto this particular circuit, the rotor is not moving, and therefore for this test the slip is equal to 1. With the value of slip equal to 1, the rotor resistance is just the value of the R2, and R2 is a very small value because it corresponds to the shorted bar resistances which are available inside a rotor circuit. Now, because this R2 and X2 are so small, so what happens is that majority of the current which is flowing from this I1 moves onto the rotor circuit. Instead of diverting onto the magnetizing branch as we have seen in the previous test. So the overall circuit, if we ignore this IM here, for this test, this IM is much smaller than this I2, and therefore the overall circuit seems to be a series circuit. Now, with this thing in mind, with this test, we have one problem. The problem is this, that we have locked this rotor, so the rotor frequency is now equal to the electrical frequency. However, in a real environment or in a real operation of an induction machine, the rotor frequency is equal to the slip times the stator electrical frequency, and the slip varies over the torque speed characteristics as we have discussed just shortly. Therefore, this test do not gives an accurate picture of the behavior of the rotor circuit in a given induction motor. So there are several things which should be kept in mind before we undergo this test, and usually we go for a compromise such that we use a frequency which is 25% or less than the actual frequency of the line, and therefore we are using this variable frequency, variable voltage 3-phase supply. So the 25% means that for a 50 hertz supply, instead of supplying it at 50 hertz, we are supplying it 12.5 hertz, right? This is we are supplying around 6 or 7 hertz for that 50 hertz supply, which correspond to the 25% value of the of the stator frequency. Now, after we set up this test voltage and test frequency setup, first of all we set the variable frequency, and thereafter we set the variable voltage such that it corresponds to the rated current of the motor. Now, once we have these things done, then the power is measured, which is equal to under root 3 VTIL cosine theta, from which we can find out the power factor, which is equal to cosine theta, and that is equal to the input power divided by under root 3 Vt into this IL. So the magnitude of the total impedance under the locked rotor test ZLR is equal to V phi over this I1. What is this V phi? V phi is the terminal voltage Vt, and this I1 is equal to under root 3 times the IL. So the ZLR, this ZLR is equal to the RLR plus J into X dot into this LR, that is equal to ZLR cosine theta plus J ZLR into this sine theta. In this particular test, the locked rotor resistance RLR is equal to the sum of this R1 and this R2, because this current IM is approximately equal to 0. So total resistance in a locked rotor test is equal to the sum of this resistance R1 plus R2, and similarly the reactance, which is the locked rotor reactance X dash LR, is equal to the X1 dash plus the X2 dash, where the X1 dash and X2 dash are measured at the test frequency respectively, not at the rated frequency. So now the value of this RLR, which is the rotor resistance R2, can be calculated by using the resistance R1, and this XLR is equal to the locked rotor impedance is equal to F rated divided by the F test into X dash LR, and that is equal to X1 plus X2. Now remember that unfortunately there is no method through which we can segregate the value of this X1 and X2. There is no such method available so far. For this R2, once we know what is this RLR, which comes from this particular expression, the R1 is still unknown, and therefore we cannot identify this R2. But fortunately, by having another test which is known as the DC test, we can find out what is the value of this R1. And this DC test is quite similar to that of the transformer test that we have seen earlier. Now the DC test says that DC test is used to find the value of this R1. Now why we are interested in finding the value of this R1? So that once we get the value of R1, we can subtract it from this RLR, which we obtained through the locked rotor test, and thereafter we can identify what is this R2. Now the value of R2 is very critical because it identifies and it plays an important role in defining the starting torque of a machine, and it shapes the torque speed characteristics of a given induction motor. So in a DC test, we provide a DC voltage to the starter circuit, and we provide a DC voltage to the starter circuit. For the sake of safety, just use some resistance here as well, which acts as a current limiting resistance. This is also a variable DC source. This is the ammeter, and here we are measuring what is the voltage here. Now because we are supplying a DC to the stator circuit, so consequently there is no magnetic field which is revolving, and consequently there is nothing which is induced in the rotor circuit. So forget about the rotor circuit. The only thing which is left is the stator circuit. Among that stator circuit, because we are operating the DC, therefore the impedances which are present due to the reactances of the stator circuit as well as the magnetic circuit, both are gone. So what we are left with is only the resistance of these two coils, and we do know that the amount of current which is flowing here depends on the value of the resistance, the DC resistance which these two stator coils offer. So for this we can say that this 2R1 is equal to this VDC over this IDC, and therefore R1 is equal to VDC over 2 times this IDC. So this test provides us a way with which we can find out the stator copper losses at no load. It also provides us a way to determine the rotational losses that can be calculated as a difference between the input power at no load versus this stator copper losses. So in this particular test, you can see that we have this particular equation. Once we get what is the value of this R1, we can also find out what is the stator copper losses here, and thereafter this P input becomes equal to the rotational power losses here. So this R1, determination of this R1 using this DC test is providing us advantage on two sides. But there the point here is that this value of this R1 is not an accurate value of the stator resistance, because under real circumstances the AC is supplied. However, in this case the skin effect is ignored. So there are certain examples that I advise you to undergo. For example, look on to this example number 6.8, and thereafter the subsequent problems which are provided in your textbook, like problem 6.20, 6.21 and other examples which are pertaining to the induction motor topics that we have studied. So that's all for the induction motor. Thank you very much. Allah Hafiz.